All right, guys. So, did we have a good break? Oh, no, long enough is the rest of your life, and that's not going to happen. All right. So, because I didn't get any questions, like I said, I'm assuming that either the homework was very easy or you didn't do it. And since it's due tonight, what I want to start with is field any questions that you have on any of that material. Yes.
For the equation, d sine theta equals lambda m. What does the m stand for?
M is the number of wavelengths. So if I'm looking at this, when M is 0, then I should get a bright spot. When M is 1, I should get a bright spot. When M is 2, I should get a bright spot. When M is 0, the bright spot, I guess, will be known as the center bright spot. So M literally means this. If I've got the two rays coming from my shoulders and hit dead center, what's the path difference?
Will it be?
That's the 0.
Okay.
There's no path difference because my arms, Now, if I begin to move to the side, so I could look at the screen, this one would have to go further to get to the screen. So I go from no path difference to half a wavelength, and that means I'm going to cancel. Because if I'm half a wavelength out, then they're exactly out of phase and they cancel. Does that make sense?
Yeah.
All right, because if I have this wave and I have this wave, they're half a wavelength out and they're going to cancel. So right, half a wavelength out, cancel. One full wavelength out, right.
Okay.
1.5 out, cancel. 2, right. And it just goes like that all the way across. So the M is sort of a way of counting out which bright or dark spot are you looking for.
And how does that go when you just the other side? Like when you difference?
It's the same thing. It's just that instead of this ray having to go further, this ray has to go further.
Okay.
So it's always going to be exactly symmetric. From the middle going either side, it's going to look the same.
Okay.
All right?
Thank you.
Anybody else? Yes. Sure.
When you have to find the smallest thickness of film of oil, for which
Okay. So this is one of those ones where that chart that I gave you is going to be a lifesaver, but we want to be sure we understand. And then we have, if I have 0 or 2, and I have, I want constructive, then 2 nt equals lambda. I want destructive. I have 2 nt equals m plus 1/2. When one phase changes, they flip. So we want to kind of understand where this table comes from. First off, this looks like what we would call the constructive equation, right? Because I have a path difference, and if it's different by an integer number of wavelengths, that would normally mean it's constructive. That's true if there are no phase changes, or if there are 2. Each phase change acts like half a wavelength. So if I change twice, 2 halves is a whole, so I'm off by a full integer wavelength. So this condition then is the same thing as not having any phase changes. So just as we normally expect, 2 nt equals m lambda would give constructive interference. If I have one phase change, however, when I let one wavelength out, and they should have been back in phase because one of them changed phase, suddenly they're exactly out of phase, then that leads to destructive for the same equation. So this equation will give me destructive interference if only one phase change occurs. You can never have anything that isn't in this table. 0, 1, or 2 are the only possible options because on a thin film, there's only 2 surfaces. The top surface and the bottom surface of the thin film. So either the top has a phase change or it doesn't, or the bottom has a phase change or it doesn't. And that's so you can only get these three conditions. There's nothing else this doesn't cover. In the same breath, then, if I want destructive interference with no phase changes or 2 phase changes, then I use the same thing that we had before. 2 nt represents what? And when I had d sine theta, what did that represent? What does 2 nt represent? There's a phrase I keep using, and if you can't verbalize it, you haven't understood anything I'm saying. Seriously. So when I say 2 nt or d sine theta, what does that physically represent? This is scary. You need to hire a better teacher. It's the path difference. it's the path difference. The only reason interference occurs is if two coherent monochromatic rays arrive at the same location. They either constructively or destructively interfere according to what their path difference is. All right. So, maybe when I say, do you understand what I mean when I say path difference? I've got a source. I've got a location on the screen. So I have two sources with two slits and a source on the screen. I take from that one slit to there. I take this slit to there. And do they travel the same distance? No, they don't. So how different? What's the difference in the two paths they travel? And if that difference is exactly one wavelength, two wavelengths, three wavelengths, I get bright spots. So that's where this is a path difference. If it's equal to an integer number, we would expect bright spots. But with thin film interference, we get phase changes which mess things up. So although we have path differences that might be 0 or 2, which should put it in phase, not 0 or 2, it's an integer number of wavelength. If I get one phase change, suddenly what should have been coherent, I'm not coherent, but constructive interference becomes destructive because I'm off by half a wavelength with that single phase change. This doesn't happen with two slits. So when we did the equation for two slit interference, all right, so I'm saying this is path difference. How is this a path difference? What does the D mean? What does the sine theta? What is D physically?
Opening the
The
sides.
distance between the two slits. All right, it's the distance between the two slits. And when we looked at the picture, and I said, all right, here's your screen. You've got a slit here and a slit here. And I look at this point here. Right, so these are my two slits, and they arrive at the screen. This distance here is D. All right, this represents the amount further that the second ray travels. That's my path difference. And if I can tie it to D, if I recognize that this angle theta and this angle theta are the same angle, so if I take a look at this, then D, which is this, times the sine of theta gives me that length, just by regular trigs. SOHCAHTOA, right? It's the opposite side from my angle, which is what I'm looking for. And so that's where d sine theta comes in. It's literally the path difference. This doesn't have any phase changes, so it's a little simpler. The path difference equals an integer under a wavelength, it's a bright spot. The path difference equals an integer plus a half a wavelength, it's a dark spot. And then you've got the range in between where it's neither of those, but those are the two that we always look at because the others, fall somewhere. We don't have any equations that help you say where is it 0.333, so we either all the way or all or nothing. This gets complicated because we have phase changes that occur. When do phase changes occur with thin films? So this represents all thin films from here to eternity because this is one side, the other side, and the film is thin. All right, so this can be anything that you can think of. So I have N1, N2, N3. All right, and this is the thin film. It's where everything interesting happens. And let's say this is air, so this would be 1. Let's say this is some kind of fancy oil, and let's say this is water. What's the rule for whether or not there's a phase change when, first off, does the phase ever change on transmission?
No.
No, good. It changes on reflection when? Under what condition? When the reflecting surface, the new n is bigger. All right. So, do I actually ever care about any light that enters this region? No. It does, but I don't care about it. I only care about reflect from here, and then those, I'll draw that better in a minute. But so what happens is, let's come in. So light hits the surface and reflects. Is there a phase change?
Yes.
Because
1.5
1.5 is bigger. Then the light that didn't reflect but got transmitted hits here and reflects. And the question is, was there a phase change?
No.
No, because this is smaller. Everybody with that? So the first thing to do is count phase changes. So you set them up, you look at the index of refraction for all the regions, and you count phase changes. In this case, we had exactly 1. So that means I will be using this column to figure out if I want destructive, this equation, if I want constructive, I use this equation. That's what guides me to finish the problem. Now, the other thing that became apparent as I talked to several of you is that it's not really clear to you why I say that the light is perpendicular. All right, what direction does light reflect off this desk? every single possible direction above the desk that there is. All right? So if I blow a soap bubble, what direction does the light reflect off the soap bubble? Every direction. But the only directions that matter to what I see are the directions that are normal to the surface. And the reason for that is fairly simple. If I draw a ray that comes here, which then reflects, all right, some of it refracts and goes in and reflects, and then some of it transmits. So what I've got going is light comes in here and it splits up. Some comes back, some goes in, I can draw those arrows cleanly, and then some goes all the way through. You basically see this going on, right? What happens when the blue light, it's not blue, I'm using color for not because it represents a wavelength, but because it's what's going on. When we get here, it's going to also transmit, all right? Now, are those two rays on top of each other? No, they can't interfere with each other. I draw it this way because this picture is really boring. I can't see that this is happening. I can't see any of this happening because they're all right in a straight line. So I tilt it to the side so I can see what's happening, but it's not like this. It's like this. Does everybody understand that? So that then this thickness, which is T, all right, that's the thing that we're looking for. But the problem is, so the path difference, ideally, when we look at how much further does the blue light travel than the white light? So in my picture, if this is T, it goes T down and then T back, and so it's 2T, right? Yeah, so that's where the 2T comes from in this equation. But what's that n doing? Well, the problem is, what we're interested in counting is wavelengths, and the length of light changes in the film because n is bigger than 1. So the n factors in what the new wavelength is. All right, that's what that n does for me. So the path difference is 2nt. What we really are saying is that 2t is equal to m lambda over n, because this is the new wavelength in the film, lambda divided by n. I just bring the n to the other side for convenience, but that's what's going on. 2t is the path difference, and it's an integer number of wavelengths in the film where the wavelength is reduced by the index of refraction.
So let's say on the test, are we going to be given that kind of chart, or we have to know that?
I'm not giving you that chart.
Okay.
You can reconstruct it on your own. I'm not giving it to you, because if you don't have it learned by the time you do your homework, you're not paying attention.
I'm sorry, what did you say n stands for again?
N is the index of refraction of the thin film. All right? I'll have to sort of think about that, but really, there's nothing to memorize. Here's the thing, is this is the same thing as ever, is that, 2nt is a path difference, equal to m lambda. 2nt, m plus half lambda. These are the same idea as what we have there. It's the whole heart of what we're doing here. This chart comes from the fact, do you understand phase changes? So you can construct the chart for yourself if you think about it. If I have 0 or 2 phase changes, then the pattern is exactly the way we're used to. This is constructive, this is destructive. A single phase change just flips it, so it just takes those in terms of the other side. I could cave, but I wouldn't count on it. I need to threaten you that you need to know it. All right? So, when we take a look at this then, what's really happening is all straight on top of each other, but it's actually occurring, I draw it to the side so we can see it. I don't care about the transmitted light, it's never coming back to my eye. Right? So what I care about is what's the phase relationship between the reflected from the top surface and the reflected from the bottom surface. That's what takes me to my chart. When they ask me for the thinnest film for which a certain light is destructively interfered or is anti-reflected, what does anti-reflect mean? That it doesn't reflect, which means it is destructive, right? So we're looking for destructive interference. So what you would do is you'd come to this equation and you'd say, what's the smallest value of m for which I would get, for which I can solve this? And that's the thinnest one that'll make it happen. Now in this case, where I have one phase change, and I want destructive interference, what's the thinnest I can make? So I come here, and I've got one phase change I want destructive, so this is my equation. What's the thinnest I can make it? 0 or 1. 0 actually does occur on the top of soap bubbles just before they pop, but it's really not good construction because even a tiny puff of air will break it or whatever, right? So typically use 1. If I get 2 changes of phase, so that, let's say this is reversed, or let's just make up numbers. So this is 1.25 and this is 1.4. Now how many phase changes are there? 2. All right. So I would come to here and I would say I want the thinnest one that will cause destructive interference, and that would bring me to here. And now what value of m do I choose? Now I can choose 0. All right. So what happens, as I told you before, this is something that happens all the time, is that then you say, therefore, T is equal to 1/4 lambda over n. And so this is the effective wavelength, and that's 1/4 of that. And it's called a quarter wave coding. You'll hear it, if you're ever in anything to do with lenses, you'll hear it referred to all the time. Sunglasses with the fancy stuff that takes all the glare away if you go skiing or something. They're called quarter wave coatings, and they cost a little more if they're done right. Yeah.
Why did you choose 0?
Because I want the thinnest. Because if I'm going to coat a piece of glass with a really expensive chemical, which it tends to be, I want to use the least that I need. So I'm looking for the thinnest film that will do it. And so I choose 0, but if I chose 1, it would work. But it cost me a whole lot more of that chemical that I have to put on. Right? Is that a question waiting to happen?
Yes, so for the first one, you said that you can use 0, but it won't happen, right?
It's because what it means is you have no thickness at all. So it has to be so thin, it has to be just a couple atoms thick, and it's really hard to try to manufacture anything that's a couple atoms thick. So 0 is not going to be a good choice. 1 is what we choose.
And then the bottom one's will be 0.
We could choose 0 because 1/2 of a wavelength is now no longer negligible. That's actually something we can do. Yes?
Can you explain that again? I
Which-
just don't get why you have to use 1 on the first one and then 0 on the next one. I just don't get how you...
Oh, if I plug in 0 here, it tells me I have no thickness at all.
Okay.
And there actually isn't a thickness. It gets close to 0, that will work, but you can't build it. Because how do you build something that's only a couple atoms thick?
Okay.
You can't do it. So it's a construction kind of thing. A soap bubble does it naturally. If you blow a soap bubble and watch the top, as it evaporates, the top eventually becomes just a couple molecules thick, and all the colors get canceled. But it pops right after. So it's only that way for just a few brief seconds before it pops, because at that thin, it can't last very long. But so 1 is what we choose here. I can choose 0 here because I have the half.
Oh, okay.
All right, so if I choose 0 there, it's still not multiplying by 0, I'm multiplying by 1/2. So I can choose 0 without making it disappear. So we good on that?
Yeah.
All right. So, kind of lost where I was going. Actually, I guess that's basically it. So, the thing is, they asked a lot about destruction. When it comes to thin films, you will almost always be asked to find cases of destructive interference rather than constructive. Do you know why? Because in typically white light, you don't see patterns due to the destruction. Due to the constructive interference, you see the pattern of light that occurs from destruction. So it turns out if I have white light and I completely remove a color, the new color that's created is what I see. But if I enhance a color, it may be enhanced, but so are all the colors near to it, and so I don't ever really see that color. The color that we see is always rainbow colors minus a color, and so that's why the colors on soap bubbles are distinctly different than the colors of the rainbow. If you ever take a look at them, or we talk about, and what was the word I told you we call the colors on soap bubbles? That whole week where we got to forget everything I ever said. Starts with an I. IR, iridescence. All right, it's a word you want to know. It's actually a cool word to understand. So you have iridescence, where it's white minus 1, and we have rainbows, which are just bright colors of themselves. All right, so in any kind of thing doing with thin film, one thing you want to understand, you can have film out of anything. It doesn't have to be oil. It doesn't have to be a uniform thickness. And one of the things you're going to see in lab today is, by the way, the name of the lab today is Optic Circus, but we're using circus in the true Latin sense, which just means go around and around and look at stuff, all right? So I talked about this last time, but I want to be sure that you're remembering. So I had 2 pieces of what we call optically flat glass. If you put a human hair on one side, then the thin film involved is air. All right? Then the thin film is air between the 2. Do you know what I mean when I say 2 pieces of glass are optically flat? Real glass is especially those of us who don't have millions of dollars. Have you ever stood kind of far away from a relatively cheap mirror and you look deformed because cheap mirrors are not flat? If you're close, it doesn't matter, but if you got far away, it's really, it's like at circuses, they have these malformed mirrors to make you look strange ways, all right? If the glass isn't flat, it distorts the image, and the further away you are, the worse it gets. So in astronomy, when you're building a telescope mirror, you need the glass to be optically flat. The shape that you make it needs to be within what we call a quarter wavelength. It has to be as flat as it almost can possibly be measured, or else the image gets distorted. So what happens here is we need optically flat glass, because if it's not optically flat, none of the things I'm talking about will happen. Because what would happen is we wouldn't have uniform, the glass would be like this, and the distance between the two pieces is not any pattern that I can come up with. But like this, what would happen is, when I look down at this, what do you expect that I would see? So I've got light shining on these two optically flat glasses with a human hair separating them on one edge. What should I see when I look at this? By the way, what's really funny is when I first tell students to look, they don't see anything. And then after they look at it for a while, they go, oh, how come I didn't see that first? I don't know what it is. It's like the brain doesn't want to see it, so you have to look for a while, and then it's there, and you learn to look at it. It's kind of like partly you have to learn where to focus or something to see. I don't know what it is. But once you see it, then you see it every time you look. But almost nobody sees it instantly. I don't know why. But the idea is you see a whole series of bright dark lines. Why? So it's just it's bright dark, bright dark, bright dark, bright dark. Uniformly spaced all the way down a piece of glass. Why? Because the thickness keeps changing uniformly. So it's 25 wavelengths off, 24, 23, and then in between it goes as 25, 4.5, 23.5. So it goes from constructive to destructive, constructive to destructive, constructive to destructive, all the way down, because the distance between the two pieces of glass is constantly changing, hence the thickness is a different multiple of the wavelength of light. Now that doesn't work in white light, because why? If you've done your homework, there's a series of things we have to get interference going on, and they are what? There's three things.
Polarized.
It has to be what?
Polarized.
Not polarized.
Monochromatic.
Monochromatic. Okay, it has to be monochromatic. Is this monochromatic? No. Okay, that's out. So I need monochromatic. I would also need coherence. All right, and finally, all right. So it turns out that that's not as you need to be kind of far away from the two slits. All right, so the distance needs to be large. With this kind of thing, this is the width of human hair. You'd be hard pressed to get your eye close enough for this not to be a large viewing distance, right? So we're going to get those. So what we use is a monochromatic source, a sodium source, and it works just fine for doing this. All right, so we can see that. Trying to think if there's anything else I want to be sure. All right, so here's the other thing. What we were doing last time, I introduced the idea of diffraction patterns as opposed to interference patterns. Has anybody got any lingering questions on this, on the thin film? All right. So I talked about diffraction patterns and interference patterns. What's the difference? And let's just start there. So what causes a diffraction pattern? You guys do realize that the homework's due tonight, and if you don't know what the diffraction pattern is at this point, you're going to be hard pressed to finish this homework. It's not easy. It's easy if you understand it, but if you can't answer this question, then I don't know if you understand it. I'm scolding you, by the way. Hope you had a good break. All right, so what causes a diffraction pattern? Let me start here. What causes the interference pattern? Let's assume that we got the coherent, all that other kind of stuff. What do I need to get an interference pattern? 2 or more slits. Everybody with me? I need 2 or more slits, and the light from each of those slits interferes with the other light where they land on the screen. Because once I've got 2 slits, where does the light from one slit land on the screen? I say I've got 2 slits, but I'm shining on this. Where does the light from just one of the slits? Where does that light land on the screen?
Screen.
What's that?
Screen.
On the screen. So I've got a screen being a wall, whatever. I've got 2 slits, light coming through, I'm landing on the wall. Where does the light from this slit land on the wall? There's a single word. Everywhere. Everywhere. Where does the light from that light land in the room? Where does the light from my hand land in the room? Everywhere. So from this slit, light lands everywhere. How about the other slit? Where does it land?
Same.
Everywhere. So why do I see a pattern? Because if it's coherent monochromatic light, at each point where they land and they're off by a half wavelength or some multiple of that, I'll get dark spots. And if they're off by integer number wavelengths, I'll get bright spots. But the light is literally going everywhere. It just happens to cancel at those locations or enhance at those locations. Do you see where I'm going with this? All right. So what causes interference pattern is multiple slits, because I've got light from each slit landing everywhere and then interfering, which is why it's called an interference pattern. What causes diffraction? A what? Okay, but what causes diffraction, or what do I need to have diffraction? A single slit. Why does that cause diffraction? In other words, to get diffraction, we're seeing definitely on diffraction, we definitely still see bright and dark spots, right? So that implies some sort of interference going on, but I only have one slit. Why would I get patterns going on from a single slit? It's actually a good, you're half right, in the sense that, I mean, you've got the right idea, but it's not other sources. Within a slit, how many rays are coming through? Infinite. Do they all travel the same distance to get to a single point in the room?
No.
That's the key. So what happens is infinite numbers of light rays are coming through, but certain points, all the rays are off by a certain amount, and it makes a dark spot. Right? And other places we get bright spots. So it's the fact that rays come from across the entire width of the slit and give me a pattern. All right? And that pattern, the diffraction pattern, looks distinctly different from the interference pattern. The way the diffraction pattern looks is like this. So we've got a big wide band in the middle, and then evenly spaced dimming bands on the sides. And the derivation of this, as I told you, is I showed you how to figure out how to figure out where the first dark spot occurs. Subsequent dark spots get a little tedious without teaching you much. But so this happens because of the diffraction, simply the slit width. But what determines where the first dark spot is what? How do I know where that first dark spot is? So I have A sine theta equals m lambda. This equation looks an awful lot like this equation, doesn't it? Well, what's this equation for? Two slits, right? And this is for diffraction, and they have completely different meanings. Is this a bright or a dark spot?
Right.
Is this a bright or a dark spot? Dark. And it's really, really important to keep that straight. They look the same, but they're entirely different. What does D represent here? The slit separation. What does A represent? The slit width. A represents the slit width. How wide is the slit? So guys, here's a logic test. Can I make an interference pattern without diffraction occurring? Let's say I want the simplest. The simplest interference pattern is how many slits? The simplest. 2. Can I make a 2-slit interference pattern without having diffraction? No, because
I have one each.
all real slits have
Different.
width. You with me?
Wait, can
You can't make a slit that doesn't have a width.
Oh.
And since this is the width of the slit, if I've got a slit with a width, I've got diffraction.
Doesn't mean diffraction contributes to it.
You can't make it without diffraction. Diffraction occurs no matter what you do. You can't make a pure interference pattern. I can make a pure diffraction pattern by only having one slit. But if I have 2 slits, I get interference, but on top of that, I've got diffraction. I can never get rid of diffraction. Does the door act as a diffraction slit for sound?
Sure.
Is sound a wave?
Yes.
Yeah, and is the door a slit? And it's a single slit, and absolutely diffraction occurs, which is why somebody sitting on the steps can hear me. Because the sound diffracts as it goes, bends as it goes around the thing, and lands in all the places down the hall. All right? So we definitely have that going on. Now here's the next question. Is it ever possible for A to be larger than D?
Sure.
Say what?
Yes.
No, because? It's not fair, but when you see the answer, you're going to kind of hate yourself. Just because it's science, we turn our brains off for basically stupid things. I'm not calling anybody stupid. I'm saying that we just don't think of it in the most basic terms. Slit, slit. Width, separation, right? Okay, think about this. Separation goes from the center to the center. That's my D, and this is my A. Can I make A bigger than D? What just happened? I got one slit out of that. In other words, if A gets big, if the width is bigger than the separation, they overlap. You don't have two slits. So, but if I go here and make them really wide, the whole point is this is my D and this is my A. That if A gets bigger than D, then the edges overlap and I only have one slit again. You can never make A bigger than D or you don't have two slits. All right? So the point is you can never ever get that situation. So you're always going to have more than one interference pattern in the middle of your diffraction maximum if you've got two slits. You're always going to see something. All right? And so we're going to look at this in class today. What I've got is there's two lasers set up little screens, and you can turn and you can watch what happens as a single slit gets wider or narrower. There's a little thing you can turn, and as you turn it, it changes the width, and the laser shines through, and you can watch the pattern on the screen. You can then put two slits in, and you can watch what happens as the separation. So it's got two slits. There's a little groove where the slits go apart like that. So you shine, and you can watch as the slit separation changes. You can watch what happens. But the point of the matter is that what happens is my interference pattern overlays this. So what happens is that the middle one, and sometimes two and sometimes three on either side will show up, but where there should have been an interference pattern here, the diffraction pattern kills it. And it's an intensity game. If diffraction is 0, 0 is what you get because anything times 0 is 0. If interference is 0, even if the diffraction pattern wouldn't have been, it goes to 0 because, again, so we see bright dots with dark spots in the middle of the diffraction pattern because 0 times anything is 0. So it's only when diffraction and interference are both constructive that we can see it. So if you remember how it looked, and we'll look at this again in the lab, but if you remember how it looked, we saw a bunch of bright spots, and then we saw sort of a dark spot, and then the bright spots started up again, and then dark spots, and then they started up again, and so what's happening is this is the minimum of the diffraction pattern, and it wipes out the interference pattern. These are the minima for the interference pattern, and it wipes out the main width that the diffraction pattern would have had. I'm not asking you to do any math, I'm just asking, can you make that picture? Can you? No. All right. So, first off, do you understand that the diffraction pattern is going to have a big wide bright spot in the middle, then a gap, a minimum, and then another bright spot, and then a minimum, and then another bright spot. All right. So, and the diffraction minimum, maximum tend to be kind of wide. The interference patterns tend to be very small. So they overlay each other. So what I'm going to say then, let's see if I can make this easier to see. Here, there is the diffraction pattern. Just look at it. Can you look at that and tell me that's a diffraction pattern, not an interference pattern? Can you look at that and tell? What's the key? What do you see that you know it's not interference? The middle one's wider. All right. When the middle one's wider, that's diffraction because interference doesn't have a wider middle spot.